Hey folks, welcome back to Walter's Aircraft Works. It's May 16th, 2017. This is episode 3. We're calling it drive coupling. We're going to try to build a drive coupling to connect the output shaft of the motor to the input shaft of the transmission. I told you last episode that I've been cheating a little bit, doing a little bit of research, ordering some parts, just trying to get ahead of the game here and keep this thing rolling along. So let me get you caught up, show you what I've done, what we need to do, and let's try to knock this thing out. I ordered a QD coupling with a little bit of research on the internet. I noticed that people were using all kinds of different couplings, Lovejoy couplings, these QD couplings. I originally thought that I was going to machine my own coupling. I believe I mentioned it in either episode 1, maybe it was the intro, but I've always wanted to do some broaching, and I don't have any broaching equipment. I would still like to do some, but when I started researching it and looking for the equipment, it's not cheap. Doesn't mean I'm not going to buy any. It's hard to justify spending the money right now when I bought this coupling from Global Industrial Supply, $12. I think by the time I paid the shipping, it was probably $15 to get it here to the house. Unfortunately, it's made in China. I guess what did I expect for $12? But jets in. Hey, sorry about that. Putty tap interrupting my rant on Chinese goods. So we were talking about QD couplings, and like I said, I bought this one off the internet, and well, let's just take a look at it. I've obviously had it open before. I've been kind of doing my homework here and figuring out how to cut tapers, and I've never cut tapers before. But what is a QD coupling? Well, this one is 1 1/8" inside bore with a keyway in it. It's already been broached in there for us. The outside of it is a flange with a taper on it. Originally, when I did the internet research, people were saying that this was a 4-degree taper. I cut my prototype here with a 4-degree inside taper to it, and it didn't fit well together. I had to go back and kind of mess with it and measure, do some more measuring. Turns out I think it's a 2.5-degree taper. Again, might be machinists all over the world screaming at the monitor saying, no, you idiot, it's, I don't know, 2 degrees here and 2 degrees here equals 4 degrees. I don't know, maybe something like that, but I got it to work. Set my miter up on 2.5 degrees, cut the taper in there, and it fits together really well. I wound up kind of whittling away on the face of this stock until I got it to fit nicely. When I put the bolts in here, put it on the shaft, tighten it down, this face of the stock bottoms out on this edge of the coupling, and it gets nice and tight on the shaft, and the run out of the thing is less than 1/2 thousandths of an inch measured right here. So I think that's going to work well. I'm a little bit disappointed that there's only 3 holes here. These holes are obviously, when you can use this coupling for several different installations, and I'm guessing that you could run the bolts through this way into a threaded fitting on the other side. This is kind of a universal part, so you could run the bolts either way. I think is the reason why these are through holes here and these are tapped holes. But I still think we're going to be able to use these holes to our advantage. We might wind up running some bolts back through the other way and still utilizing the holes. All right, so what are we doing with this thing? We need to connect this QD coupling to our splined coupling that we're going to pull out of or harvest out of this clutch plate. We need a pretty good size flange to attach this if we're going to utilize these rivet holes, which are about 4 inches on center, we're going to need a pretty good sized flange. The round stock that I had wasn't big enough for that. Here's the round stock that I have. It's 4.5 inches in diameter, and I think it's going to be good to the end that's going to attach to our QD, but it's not quite big enough to pick up these 4 bolt holes that we're going to create, or that we're going to use for this inside spline coupling. It just wasn't quite enough edge distance for my comfort. So I did find this plate. It's a piece of, well, I think it's, move you back here a little bit. I think it's an inch and a quarter. Somebody else started a project with it, drew a 5-inch circle here on it, and then started to trim on it, and went a different direction, I guess. But that's good news for us, because we'll use it. We can crisscross, find the center, cut a 5-inch, approximately 5-inch circle out of it, create a flange to pick up those 4 holes, and then bore a hole in the center of it, create the other part of our drive coupling out of this stock, and turn some kind of protrusion sticking out of here that we can shrink fit into this, heat this, and cool this, press it together, and let it normalize temperature, and then really lock it down with the bolt holes, or the bolts that go through all of that into this QD coupling. And I think we can make a really solid coupling out of this material, and hey, lucky for me, I just happen to have it. So that's my plan. I hope all of it works. We got, you know, enough of this material that if I make a mistake or two on it, I can recover from it. This is the only piece of this I have, so if I screw this up, you know, be back to eBay looking for some more stock. That's the direction I'm headed, and let's get going. Okay, I was scrounging around the workshop here trying to figure out how I was going to drill these rivets out, and I think I came across a good idea here. Actually fairly lucky. This is a mandrel that I made for cutting some bushings for another project. Actually, I've used it twice now on 2 different projects, and I think it's going to work well for us on relieving this clutch plate of its spline coupling here. Looking at it up close, I think I want to take these rivets off right here, which is going to take the friction material off, and then we'll be able to trim this disc, or this stamped piece of steel, back to the same diameter as this one, and that's going to make a nice package. Then we can drill these rivets out for clearance for our bolts to go through to hold it to our flange that we're going to have to create. So when I found this mandrel that I'd made, it looked like it, you know, it's a little bit too big here, but I made it with a tapered aluminum bushing here, and I think that's going to help us center it up. So we should be able to just run it in like this, tighten it on down, and then chuck it up in the lathe using the mandrel, and then turn it and just turn these rivets off. And hopefully once we get it down to the stock, we'll be able to push those tabs off the back, get rid of the friction material, and then we'll have to come in here with a tool, turn this down a little bit smaller in diameter to match this one. So let's get it set up in the lathe, tightened up, and see how it works. All right, here we are, chucked up in the lathe, and hey, I want you guys to tell my wife this is the reason why we throw nothing away. Look at that, fit perfect. Runs pretty true as well. Just rolling it by hand. You see a little bit of wobble here in the friction material, but the center of it looks like it runs pretty true. So I think it's going to work real well for us to just come in here with this facing bit and just chip away at these rivets. Hopefully they're not too hard. Hopefully we can just chip away at them and whittle off those rivets. I think it's getting the job done. A little bit more. Alright, let's get it over to the bench and see if we can knock those rivets out. Well, it didn't work so well. It took the heads of the rivets off, or the shop end of the rivet off, but they're squished in there pretty good. I've taken the punch and tried to knock them out, and they're not falling out of there, and I'm afraid if I put too much pressure on them, it's pretty hard to support the back of this thing. If I put too much pressure on it, hit it too hard, it's going to start warping this plate. So I think the plan is now I'm going to take it over to the bandsaw, and I'm going to cut in here and just try to cut these fingers off with the bandsaw, and then chuck it back up in the lathe with that mandrel and start turning it down till we get it. And I think it's got to come just south of these holes right here to make it match up with this side. So let me give that a try. All right, well, we made a mess out of that. Didn't cut very well, and it was pretty stinky. But we got it off of there, and now we can chuck this back up, use that mandrel, put it back on the lathe, and hopefully trim this edge off down just shy of those, the bottom of the holes there, and it should clean up. It'll be pretty nice. All right, we got it trued up, and it was a little bit more difficult than I thought. Those little tabs that held the friction material on there were some tough stuff. It was ferrous metal, but it must have been tempered, because it was tough to cut. But we got it all whittled off of there, and then I bumped it up against the belt sander and brought these two to the same diameter, and I think it's going to work well. Now the next step will be we'll probably go through the same type of process we did cutting the spacer rings. We'll drill a 1/2 inch hole in the center of this, mount it on the turntable, and cut this thing round, or fairly close to round, with the mill. And then we're going to have to figure out how to mount it on the lathe to true it up and make it clean. And then we'll have to counterbore or center bore this hole out to whatever dimension we decide that we need it to be. So that's the next step. Okay, we're over here on the mill, set up with the turntable again. This is going to be a real similar process to the way we cut the spacer rings. We did drill through the material and run our bolts, our securing bolts, into the T-nuts through the material. I think that's going to give us a real solid setup. We should be able to lower the mill head slightly and then run the table this direction till we bump up next to the line, make a rotation, plunge down a little bit more, and just continue that process. Obviously, when we get down almost through the material, we're going to lose the support of these bolts. But once we do so, even if we get down and leave a 1/16 of an inch of material or so, we can zip that off with the bandsaw and then clean it up. We're planning on cleaning up the outside of it with the lathe anyways. We're just trying to we're trying to turn this square block into a round block so we can put it in the lathe. So I won't show you the whole process. You know how it works. We'll do a round here and then finish it up off camera, and we'll bring you back in when it's time to put it in the lathe. Okay, we worked our way about halfway through the material, maybe a little bit more than halfway, and we decided before we lose the support of these bolts that are holding us down, we're going to go ahead and cut the grooves in the top of this flange to create the relief that we need for our springs here. It's about 200 thousandths is what I mic'd them to be, and we're going to cut it a little deeper than that, maybe a 1/4 inch. 2.50 or 0.250, 1/4 of an inch, to give us a little bit more relief. And it's going to take several passes with this 1/2 inch 4-fluted mill head, but I think we can cut it, do a couple of passes, make channel, and then rotate the table another 90 degrees, and then make the passes for the opposite springs. So we'll bring you back in when we get these cut, show you what we're talking about. All right, we cut one path. Actually, it took us 5 passes, I guess, to cut this groove in here. And it turns out There's two different widths of springs here, and if you stare at it long enough you can start to see it. These springs are bigger in diameter but shorter. These springs are smaller in diameter and longer. So we've cut the path here for the longer ones. Now we got to come back 90 degrees and cut the shorter path ones. And we're all set up to plow through it the first time. It's about half depth, and we'll make 2 passes to get it completely to depth, and then we'll start moving the table each direction to clean out a wide enough width for this the shorter spring. So here we go. A little snafu there with my videoing. I ran out of memory as we were milling these slots in our flange here. But as you can see, it's all done, and they came out pretty nice. It fits well. It drops right into the little slots. It'll drop a little bit deeper once we get these rivets taken out. But I think the next step is to chuck it up in the lathe. You can see we cut it out kind of oversized to give us plenty of room to clean this thing up. Cutting circles on the rotating table there with the mill doesn't leave a real clean surface. We could have moved the mill bit in a little bit closer and taken a couple more rounds and cleaned it up even better, but the intention was all along to put it in the lathe and clean it up. And that's what we'll do next. We also need to lay out for these holes so we can drill through it and be able to run some bolts all the way through this whole assembly. So to the lathe next. Hey, we're set up over here on the lathe, and I've chucked the part up in the jaws with the jaws flipped around to grip it from the outside. The more I look at it, the more I just don't like this setup. This outside edge is way too rough to be close to being centered with our hole here. So I'm going to change this around. I think I'm going to go back to a mandrel setup. May even use that same mandrel that we used before. I probably have to turn the center down just a little bit to fit in this 1/2 inch hole. But if we center up on this center pin, that's going to leave us a lot truer out here on the outer edge, in reference to this register of the center hole here. If we try to true it up here now, I don't think we're going to be, the runout's not going to be good between the outside and the inside hole. I didn't explain that very well, but I think you'll see as we move along that if we always keep this center hole as our reference point, the whole thing's going to run truer. So let's change this around and set it up on a mandrel. I think we'll have better results. All right, we're set back up on the lathe here with the mandrel. I think this setup's a lot better than grabbing it from the outside. I think it's going to true up real nice. We're not real concerned about this outside dimension. It's not a critical dimension. We really, right now at this time, just want to true it up, clean it up, a reference to our center hole there. So I'm going to run this nice and slow as far as how much material we take off. Take lots of passes, thin passes. There's not a real, lot of gripping power with this mandrel. So I don't want to force too much, don't want to put too much tool pressure on. Just clean it up. That's our goal. All right, well, that worked pretty well. Cleaned it up nicely. I ran a little bit of Scotch Brite over it after we finished with the final pass, and it looks pretty good. You can see we got a lot of clearance in here. These plates will drop down the thickness of the heads of those rivets, so the springs are going to drop down in the grooves a little bit farther, but still plenty of clearance in there. I think the next step we're going to do is drill these rivets out and then see about lining up our plate, or how we're going to index our plate to our flange here, and then drill those holes. You also need to make some decisions about what kind of bolts we're going to put in here. I'm sure I'll use a flange bolt, grade 8 flange bolt, but whether we're going to tap this aluminum or drill it all the way through and just put a nut on the back side, that's the way I'm leaning. If we do that and use some kind of steel lock or fiber lock nut on the back side, we won't have to worry about them backing out. Let's figure out how we're going to index these holes. I guess drill the rivets out first. Okay, there it is. A little tougher to get those rivets out than I expected, and the rivet shank is still stuck in the bushing. I don't think I can get those out of there without destroying them. I'll probably make a little bit of an attempt. If not, I'll just make some. But the length of the bushing is 0.325, and the outside diameter of 0.380, and then the inside diameter, well, I haven't mic'd them, but I want to use those 1/4 inch flange bolts over there, so the inside diameter is going to need to be pretty darn close to 1/4 inch. But it fits real well now. It sits on our flange nicely. I wasn't sure whether this thing was going to spring apart when I drilled the rivets out, so I did mark it to index it, and it does come apart and goes back together fairly easy. So springs aren't under a whole lot of tension right now, not under a load. So we're gonna work now. I guess I'll tinker around these bushings a little bit, and then we still need to figure out how we're gonna index these holes using our center hole here. We need to be indexed off of this center hole to keep this thing running true. Bushings first, and then holes. Well, I had a little better idea, I think. I went over to the lathe and chucked up these bushings, the original bushings in the lathe, and just drilled out the rivet shanks. Drilled them up to 1/4 inch. Bolts fit nicely. I think that's going to do fine. Hey guys, I've been struggling a little bit about how to drill these holes, how to index the holes from the center hole here, and put it in the turntable and do some measurements. Actually use a dial indicator to move it back and forth to find the location here. I mean, I don't have a DRO on my mill, so that would probably make it real easy if I had a DRO. And setting up the dial indicators works, but I wasn't real comfortable with doing that, so I looked for another way to kind of index them. And there's a little bit of movement here. When this thing drops in those channels that we milled, it's got just a tiny bit of back and forth movement. I don't want this hole off center. I'd like to get the run out as close as possible. Obviously if it's off center, it's going to cause vibration. So this is what I came up with. I turned another mandrel or alignment jig, whatever you want to call it, turned it on the lathe so it fits in here and then goes down into our aluminum flange, and it fits pretty good. It really takes all the play out of it. I think this is going to help us. We can make sure this is in there nice and tight. Then we can use our old center finders to just punch down through these holes, which will then give us a spot to drill our holes. I also stopped at the hardware store and picked up some of these grade 8 flange bolts. This is what I'm going to use. I am going to go ahead and tap this flange. I think we got plenty of material here. We'll Loctite them in when we're doing the final assembly, and then I think that'll be good. Worst come to worst, if they pulled out or if they tend to get loose, we could drill all the way through it, drill the threads out of it, put a nut on the back side of it. But I think these will work fine. So let me get going on drilling those holes and tapping them, and then we'll go to the next step. All right, here's the setup here. We've got our stock on our turntable, toe clamped down. We're all indexed up. We're lined up to start with our first hole here. Got a little tiny starter bit in here as a pointer again. We're going to go around the 360 degrees and check each one of these holes to see how our alignment is. Well, let's see how it works. And there's the first 90. looks pretty darn good. Yeah, it's slightly outside, but pretty close. Let's go one more, the last one. Now that one pretty darn close as well. All right, so I'm gonna pilot these with this little tiny one, probably step up to a little bit bigger one, 1/8 inch bit for a just to pre-drill it, and this is a number 7 drill bit, which is what a quarter 20 tap requires. So we'll do all those, a little deburring there, chamfering the hole, and then we'll run a tap in each one of those holes. I hope I got a long enough quarter 20 tap to go all the way through that. I'll have to check that out, but let me drill some holes here and then I'll bring you back in. Well, that worked really well. It was time consuming, and I'm not quite done yet. I used a starter bit and then 1/8 inch drill bit and then this number 7 drill. Then started the tap with the mill. I didn't use the mill under power. I just turned the drawbar up here by hand with a ratchet and ran in about half the length of the tap and then backed it out. Turned it 90 degrees, did the next one, and so forth all the way around. And then I finished up the chamfering tool. And it looks pretty good. I'm going to pull it off now and then finish up tapping the holes by hand. Try to run it all the way through. I think, we'll see. This tap is certainly deep enough for our bolts that we're going to use, but I'm going to try to get it to go all the way through. May not work. May just go the depth of the tap, which looks like what I'll have to do. Or I could even grind this shoulder down some to get it to go all the way through. We'll see how that looks. Hey, there it is, all assembled. Went together real well. I didn't tap all the way through the piece. I just went as deep as the tap would go, and then lined everything up and bolted it together. And hey, check this out. Looks like it lined up very well. So real happy with this part. The next step is going to be to recreate this cup assembly and then connect the two of them together. So our drive coupling is going to look pretty close to that. It's going to be pretty cool. All right, let's get set up to machine this drive coupling, knock it out. Bandsaw's been chewing on this piece of 4.5 inch round stock for about 30 minutes now. Looks like it's cutting nice and straight, but it's sure taking a long time to get through it. All right, we got through it, and it's a little bit crooked. It's going to take some truing up there on the end, actually both ends, and that's what we're going to do now. I got it chucked up in the 4-jaw and adjusted a little bit. It's still about 30 thousandths out of center, but that's okay for right now, because all we're going to do is take some emery paper and clean up this outside, get rid of this burr, and we're going to do one side of it, swap it around, do the other side of it. We want kind of a nice smooth, well, at least a smoother surface here on the outside to get rid of the real rough stuff, so we can get it chucked up in the jaws real well, nice and secure, and not have any lumps and bumps on the outside of it. We got her shined up, smoothed up a little bit, just with the emery cloth, and now we're gonna work this 4-jaw back and forth until we get it, well, at least a little closer than that. Right now we're showing, you can see the needle swinging there, so let's back around up, make it a little easier for us. 0, that's the bottom. So we're about 37 thousandths out. We'll go back and forth with the 4-jaw and see if we can get that down to within a couple thousandths of an inch. All right, we got it down to within about, 4 or 5 thousandths of an inch there. As you can see, maybe it's 3, 4 thousandths, but that's pretty good considering the surface is pretty rough. So So certainly be good enough for us to face it, and that's what we're going to do. We're going to try to square up this end by facing it. So we'll run the tool across the end here. That's going to square us up nice and straight. Then we'll flop it around and do the same on the other side. Alright, I got it cleaned up. We'll chamfer the edge. Just knock the sharpness off from it, swap it around. Alright, now I think I'm going to turn my attention to the side. I'm going to turn some of this down just enough to true it up, and only back about an inch. What we're going to do is we're going to flip this thing back around again, and we want about an inch of it sticking in the jaws there, and we want it nice and true. It doesn't matter really how much we turn it down. We have plenty of stock to work with here, but just clean it up, true it up, give us a nice register for the jaws to sit on, and the other side's the side we're going to work down to our actual piece. And really it only needs to be 1 3/8, so about as long as this one is, but without this piece right here. So just a solid piece all the way back. So let me turn that down a little bit. Alright, now we had a pretty smooth surface to work with, or true surface anyways. It looks like it's, you know, 0.5 thousandths or something is the run out on that. So plenty good for what we're doing. We've got it flipped around in the chuck here, and got the dial indicator on it, and it looks pretty good. I had to, you know, work the chuck, center it up, and we got it within looks like about 2.5 to 3 thousandths of an inch. A lot of deformities on the surface of this. It is still the raw material, so that'll clean up well. I think we need to go back over to the bench, do a little bit of a drawing, and figure out how to attack this thing from here. Alright, so what are we doing here? We're planning on reproducing this part here and a little bit longer. We also want a piece like this that sticks out. What we're going to wind up doing is boring out the inside of this piece for a shrink fit between this piece and this piece. We'll wind up heating this up in the oven, pressing this one into it, and then letting them normalize in temperature, and then increasing the integrity of the two pieces put together. If we shrink fit them together like that, this should be pretty strong. Plus we'll have the bolts going through both pieces to help hold them together as well. We need this overall length from here to here to be 2 5/8 of an inch. This is 1 1/4 inches, so that leaves us 1 3/8 inches that we need from here to here, plus whatever else is going to protrude out to stick through here, which is 1 1/4 inches. We also, on the inside here, we want that pilot shaft from the input shaft of the transmission to fit right in the center of this, hole. So that's our smallest hole that we'll need in this this whole assembly. So I think that's where we start. We start with drilling that hole all the way through our stock, all 3 inches of it. We use this drill bit. And then we'll start creating this cupped area in here to accept our QD. This is our 2.5 degree bevel, and then we can start working on the outside dimension. Eventually we'll wind up turning the piece back around and working on the other end of it, which will be the part that we press fit into this piece. Alright, really this is the same process as we've been doing over on the mill. We're going to use a hole starter here to get us going in the right direction, right in the center of the material, and then we're going to use a this is about a 5/16 drill bit. We'll drill through it first just to kind of remove a lot of the material, and then finish up with our final size drill bit. Use lots of lubrication here. Aluminum's not real difficult to cut, but it is kind of gummy, and lubrication does help. Pretty good acid brush, huh? think I'm due for another one. All right, that does it. We're back over here at the bench this morning, taking a couple of dimensions so we can get started on boring out our cup. The minor dimension here on this QD coupling is 2.153. The major dimension is 2.190. Oh, no. Sorry about that, folks. It's a rainy day here in Georgia, and apparently you can't hunt mice or chipmunks on rainy days. So our, like I said, our minor dimension is 2.153. The major dimension is 2. Stay out of the coffee. Oh my goodness. All right, I put the cat out in the rain. Shouldn't bother us anymore. Poor cat. All right, so like we were saying, minor dimension of 2.153, major dimension of 2.190, and the overall depth here is 875 thousandths. So we'll probably bore it a little bit deeper than that, just so it gives us some room inside the cup to trim this outer face here as we kind of fine-tune this thing to make sure that this flange bottoms out on this flange at the time that it puts the proper pressure on our shaft. The inside dimension, like we've already drilled that hole, we'll keep that the same for right now. We'll probably start off by just boring using a larger drill bit here to bore this thing up as big as we can, or with the largest drill bit I have, and then we'll start using a boring bar to produce this minor dimension first, and then we can set up with the miter to do this 2.5 degree taper and get pretty darn close to our major dimension. All right, so back to lathe to make this happen. All right, here we are set up with the largest drill bit that I own. It's 1 1/8. We're going to plunge this in just shy of 1 inch to help us just remove some of this material. Be less that we have to do with the boring bar. Lots of lubrication and really slow. All right, we're set up here with the boring bar. This is a brazed in insert. Matter of fact, I just brazed on this insert. Never done it before, but been wanting to try it. I had an old boring bar here that was in pretty rough shape, and a piece of high-speed steel. It's actually a remnants of an old parting tool that I brazed on here, and I'm going to give this a try. We've got a lot of material to remove here. We got 1 1/8, so 1.125 is what our inside hole is, and our minor dimension that we need to achieve is 2.153. So what's that? 1 inch and a little less than 25 thousandths that we need to peel out of here, and I'm going to try to hog most of it out with this nice stiff boring bar, and then I'll probably switch to something that's a little bit daintier to try to create our cup with our 2.5 degree taper to it. So let's get hogging this out. Hopefully this boring bar will work. If it does, if this brazing holds, that gives us a lot of options for creating tools down the road, all kinds of different shapes of tools. So I'm hoping this works. Definitely getting the job done. May want to take it over and try to create some kind of chip breaker on it, and maybe hone this edge a little bit more. It's not leaving a great finish on the inside, but I'm pushing it pretty hard as well. So if we lightened up on the passes, it might do a little better on the finish, but I'm not real happy with the chips that are rolling out of there. They're kind of gangly and hard to manage, so a little chip breaker might be good. But I'm going to keep pressing on and see what happens. Alright, been working this thing down, got it down to about 25 thousandths, 25 thousandths to our final dimension of 2.153, and I've been periodically pulling the boring bar off and honing it and changing the shape of the cutting face slightly, and I've got it cutting pretty well. Not perfect. I think it's going to work okay for our purposes, and we're really going to change the finish when we change boring bars and start to cut the taper in it anyways. But pretty happy with the performance of it. Excited about being able to braze different pieces of high-speed steel on these boring bars. Really gives us the option to change the shape of these bars quite a bit and do a lot of different turning. So I'm going to peel off about another 20 thousandths, take some more dimensions, and see how we look and where we need to go from there, but we're pretty darn close. I've also increased the spindle speed and slowed the feed rate down to give us a nice smooth pass on this last, or pretty close to the last cut. Well, that produced some chatter in there, changing the spindle speed. I could hear a little bit of chatter. I didn't think it was quite that bad, but you can definitely see. Let's take some dimensions. Probably gonna have to clean that up, but we got plenty of material to do that. A couple more passes, cleaned it up fairly well. I messed with the spindle speed a little bit. Seemed like slower worked better than faster. And then a little bit of emery cloth and a Scotch-Brite pad. It's got it pretty smooth in there. But what it's left us with is a pretty wide hole there, and we're going to have to whittle off quite a bit off the face there to get us back down to our dimension that we need. And we actually may have to come back in here with the boring bar and peel off some more of this face to give us enough depth as well. But I'm going to change things around right now to face it. Well, I'll try to trim off enough on that face to give us the dimension we need there. And by the way, this is what it looks like. You know, just sloppy in the hole, and these two faces are coming in contact way before our tapers do. So that's what we got to clean up. Alright, there it is, folks, with a decent fit. Boy, what a struggle that was. Dang you, Keith Fenner and A-Bomb and Tubal Cain for making this machining and lathe work look so easy. It's not, it's difficult. You wind up taking a little here and a little there, at least with these tapers anyways. Wound up on the original cut of the taper, just making it too large. And you got to take a lot off this face to get it back down to the size you need. You can probably see the length of the part of the stock is significantly shorter than what we started with. Like I said, as I worked stuff off the face, or worked material off the face here, then I'd have to go back in here and cut on this face to reduce the dimension of our cone or our taper. Screwed up there a little bit somewhere along the path and made a little groove inside on the taper, and I could take that out. I could keep cleaning the taper up, but then of course that increases the outside dimension, and I would have to take more off the face and more off of this inside face here to get us back down to the right dimension, which is just chewing up more of the stock. So I'm going to leave it right there for right now. I think it's going to work okay, or I think it'll work well. The QD fitting fits right. We have a nice gap here, the same as our prototype, and it's bottoming out in the taper, not on the inside face in here. I've made sure of that. I've created enough gap in there. It's more of a gap than it is out here. So hopefully, you know, as we tighten those bolts down, it'll squeeze that QD taper or that QD fitting until this face here bottoms out against that face, and then we'll have a good true running part. Now the next step would be to take it over to the mill and drill these holes, these 6 holes, and actually probably drill a couple other holes as well to help us push this taper off when we need to. So probably a total of 8 holes. But before we do that, I want to clean this outside edge up just to give us a good register, so when we put it back in the forejaw, we can dial indicate it and make sure we get it back into the same spot. So that's next. Clean this up to the and then to the mill to drill the holes.